Bismillahirrahmanirrahim. Dear students, welcome you all to the Industrial Pharmacy class. As you know, in today's lecture, we will discuss one of the topic in the drawing chapter, and the topic titled as behavior of solid during drawing. It may be entitled as drawing wet curve. If you are asked to discuss in detail the behavior of solid during drawing process, then you have to attempt this discussion, and the title may be changed from the behavior of solids during drawing or drawing cycle, or it may be drawing wet curve. If you are asked to explain in detail the drawing wet curve, if you are asked to discuss in detail about the drawing cycle, whenever solid material is drawing, then what will happen to that particular solid material during the process of drawing. Dear students, the main objectives of this lecture is to learn about the behavior of solid material during the process of drying. If a solid material is exposed to the process of drying, then what will happen to this particular material which needs the process of drying. Dear students, after the completion of this lecture, you will be able to learn about the behavior of solids material drying, the drying cycle, or typical cycle of the drying, having the three distinct zones and the typical drying cycle. The first one, that is the initial adjustment period, that is one of the distinct zones and the typical drying cycle. And the second phase is constant wait period, and the third one is falling wait period. These are the three distinct zones and the typical drying cycle or the behavior of solid material drying. The falling wait period may be first falling wait period, and the second class of this falling wait period is second falling wait period as well. Dear students, now we will discuss in detail the behavior of solid material drying. As you know that different solid material having some content of the solvents, which may be water or any other organic solvent, and primary purpose of the drying is to remove some quantity of the solvent, which may be water or any other organic solvents, volatile or non-volatile in nature, and the goal is to remove the solvent from that particular solid, and the rate of drying, which is likewise the time of a sample, can be determined by suspending the wet material. First of all, we have to take the weight of that particular material on a weighing balance and a drying cabinet, and which may be a drying cabinet, or in another term I can say that in dryer, and measuring the weight of sample as it dries is a function of time. It means that we have to determine the rate of drying. For this purpose, we have to take the sample and determine suspended form of that particular material, and we have to note the weight of that material in a drying cabinet or on a dryer, and we have to measure the sample, the initial weight of the sample, which is a combination of the solid material as well as the solvent system, and then we have to take the sample again, and we have to note the weight when it dries as well as the time at which it dries. And by using these readings before the drying and after the drying, as well as the time taken for the drying from the sample which we have taken, that is in the solvent as well, and that particular wet solvent, solid material, the solvent comprising that is the initial and as well as the dried material. After the time to be noted, and by taking these readings we can calculate the rate of drying of that particular sample. And this can be calculated, that is the drying weight can be calculated by using the below formula. That is drying weight, in which we have to take the weight of water in sample and the kg, that is the weight taken, and the time in hour, and as well as the weight of dry solid, that is in kg. We have to take initial weight, that is comprising the water content as well as the solid material, and after the time is noted and material is dried and the dried material weight is taken, and by the difference between the two, that is the dry as well as the wet sample, we can calculate the weight of the water in the particular solvent as well as the final weight, that is the weight of the dried solid that we are taking, and the time noted for from the initial, that is the wet weight, and taking the weight of the particular dried material, and the time is also taken, which is from the wet solvent is removed, wet solid is dried to the process of the drying as well. And putting the values in that particular equation, putting the weight of the water in sample and dividing by the time that's taken for the drying of that particular material, and as well as the weight of the dried material is taken, and we can calculate using this equation. Now in this part of the lecture we will discuss the drying rate curve. That is one of the behavior of the solid during drying. It is obtained by plotting a graph of FMC, that is a free moisture content, on x-axis, and drying weight on y-axis. We have to put the values, the plotting between the graph incorporated representation, and we have to take on the x-axis, we have to x-axis and as well as the y-axis. On the x-axis we have to take the free moisture content, and on the y-axis of that particular graph we have to take the drying weight. Depending on external conditions and internal mechanism of fluid flow, that is a liquid flow, the solid material show different drying patterns. And a typical drying cycle is a drying weight curve of a solid material can be divided into the three distinct zones, namely initial adjustment period, that is the first layer zone, and the second phase, that is a constant rate period, and the third one, that is a falling rate period. Now these are the three division of the three distinct zones. When a typical drying cycle occurs for a particular solid material, is drying, then it can be divided into the three distinct zones. These are the three zones, typical drying cycle. Recalling from the previous slides, in which I have told you that if we take on the x-axis of free moisture content, and on the y-axis we have to put a drying weight for representation of graphical representation. Recalling from this, that is it is obtained, the drying weight curve is obtained by plotting a graph, and the graph is shown on the x-axis. We have to take the free moisture content, while on the y-axis we have to take our drying weight. You can see in this figure, this graphical representation for the drying weight curve or the behavior of solid during drying process. And you can see that is a dot, and then from A to E, that is the initial adjustment period, and from B to C, that is the concentrate period, and next is the critical mass charge content, that is point C, representing a critical mass charge content. And from C to D, you can see graph that is the first falling rate period. From C to E, that is comprising of the falling rate period, was that is subdivided into the two phases. From C to D, that is the first falling rate period, and from D to E, that is the second falling rate period. And this whole from C to E is termed as combinedly falling rate period. This is the first falling one from C to D, and the second falling one, that is from the D to E. And D is the C is the critical moisture content, while B is the second critical moisture content or moisture point, or second critical point, while the point E is termed as equilibrium moisture content. Recalling from the previous week lecture that I have told you about the equilibrium moisture content, and what is meant by the equilibrium moisture content. If the material moisture becomes equal to the environmental moisture, in this case neither the material gain the moisture nor the moisture is given to the environment, and that is termed as equilibrium moisture content, abbreviated as EMC. Now we have to discuss this one, the first one, initial adjustment period, that is from A to B. And this point from A to B that is termed as the initial adjustment period. That is what happened in the initial adjustment period. It is the time corresponding to AB curve that I told you, that is from AB curve, that is representation of the initial adjustment period, and it is also termed as heating up period. What happened in this period? During this period, solid will dissolve heat, temperature is increases. That is, the wet substances were kept for drying, then it will absorb heat energy from the surrounding, and the vaporization of moisture takes place, which cools the surface. When the moisture is gained, when the drying is in progress for that particular wetted substance, and it will gain heat energy from the surrounding material, and after supply of the heat energy from the surrounding, the vaporization of moisture takes place, and that is ultimately leading toward a cooling of the surface, because vaporization occurs and heat flows to the cooled surface at higher rates, and by this way, when the heat flows, it's leading toward the rising in temperature and evaporation again. And by this way, the vaporization of moisture takes place by using absorbing the heat energy by the wetted substance when it is exposed to the process of drying. This continues, and after some time, heating and cooling rate becomes equal. At one stage, the heat is supplied and the process of the heating is done, and no vaporization, but after a certain point, vaporization will occur, and at one stage, after taking some time, the process is continuously leading toward the heating and cooling rate becomes equal at one stage. After continuation of this heating energy supply, and this temperature is equal to the wet bulb temperature of drying air, and is referred to the point B on the graph. You can see that is point B that continue from the point A to B in the graph, and it shall continue up till point B on the graph. After initial period of adjustment, when temperature increases, then hot air is given and the evaporation occurs, and at equilibrium rate of heating become equal to the rate of the working, and the temperature decreases after the evaporation. While the second distinct zone, that is the constant rate period, you can see on the graphical representation, that is point BC in the graph shown, that is the constant rate period. What means by the BC? Now we have to explain this point, that what is meant by the BC, that is formed as a constant rate period. That is the time corresponding to BC in the graph, and the temperature remains constant and the rate of drying is constant. In both stages, if you see, if you supply heat energy and the temperature will be here, you can see the drying rate that will become constant from B to C, that is represented on the y-axis, drying rate. In this stage from B point to C point, it is the BC graph, the drying rate will become remain constant. What it means? That means that the temperature remains constant and rate of drying is constant. During this period, there is a continuous liquid film or layer over the surface of solid material, and that is continuously heat is supplied, and that liquid film is removed continuously. The drying rate is constant during this phase, that is a constant rate period. And this constant rate period, moisture evaporating from the surface, that is in the form of the liquid film, is replaced by the water diffusing from the interior of the solid, which having the solid contents, having the material, it is water, and it is continuously replaced by the process of diffusion, that is from the interior of the solid, and also the drying rate remains constant as shown in the curve by the region BC. So we can conclude that rate of diffusion becomes equal to rate of evaporation. The continuous film formation occurs because the material having the water content, and the interior of the solid material that is diffused, and it's similarly the moisture is evaporating, and it is replaced by the evaporated moisture is replaced by the similar diffusing water from the interior of the solid material. So we can say that the rate of diffusion, that is from the interior of the solid water content for the film formation, becomes equal to the rate of evaporation. Both are equal at this step. As the drying proceeds more, the coarse capillaries are completely depleted or deprived of water content, and the solid fails to maintain uniform film or layer of the water content, because it is difficult to maintain the water content, to maintain the uniform film, because of the deprivation of the complete deprivation of the water in the interior of the solid material. The area over which moisture film is not present, that is continuation of the uniform film is lacking at this stage, and the area and the point where the moisture film is not present, that is known as a dry spot. You can see that this diagram, that rate of evaporation become equal to rate of diffusion at constant rate period, that is diffusion one, and that continuation of film. So dry spot starts appearing and drying rate starts falling, and at point C You can see the point C that is in the graph. Point C, the drawing rates from B to C is constant, but it's starting falling from C onward, and that is termed as critical master content. Surplus for starts appearing and drawing rate starts falling, and at point C, as shown in the graph, at rate decrease and the drawing rate starts. Drawing rate becomes decreasing at point C, and at point C that is referred to as the critical master content are abbreviated as CMC. That is critical master content. One terminology CMC we use for the carboxymethyl cellulose. That is something else. That is one of the excipient. And regarding the drying process or the drying rate, one of the terminology used that is CMC. That is something else. That is critical master content of CMC. And after C, you can see the graph. That is the I'm going to tell you about the graph at C onward. You can see the drying rates is falling, and this point is termed as critical master content. And from C onward D, and from D to E, combinedly C, D, E, that is termed as falling wait period, and it is subdivided into the two phases, that is from C to D, and that point that is first falling rate period, and D from point D to E, that is in the graph, that is termed as second falling rate period, and combinedly it is termed as falling rate period. And C is the critical master content, where D is the second critical master content, and E is termed as equilibrium master content. Now we have to discuss the falling rate period, and what's happened in the falling rate period. Falling rate period, as I told you earlier, it should be divided into the two subclasses, the first falling rate period and the second falling rate period. The first falling rate period is also termed as a period of unsaturated surface drying, because the surface drying material it is not completely full of the water to maintain the film layer in the surface, and it's also termed as period of unsaturated surface drying. It is the time corresponding to CD curve. During this period, surface water is no longer replaced it will wet fast enough to maintain a continuous film or layer on the surface of that particular material, which I have told you earlier that process will be continuous, and the moisture evaporating from the surface is replaced by the water diffusing from the interior of the solid, and the rate of diffusion becomes equal to the rate of evaporation. The rate of diffusion will become less at this stage because the maintenance of the uniform film is not possible because of the depletion of water. As I have told you, the dry spots will start appearing, and the drying rate start falling at point C and will drop. So this stage, that is the first falling rate period, is also termed as period of unsaturated surface drying, because of the depletion of the water content and no longer replacement of the surface water at the rate fast enough to maintain a continuous film on the surface. And at this stage, dry spots begins to appear, and rate of drying begins to fall off. The point D is referred to as second critical point. You can see in the diagram that is the first falling rate period, wherever you can see that is the hot air is there, the diffusion from the interior and the drying part, and continuous film is not over there. You can see that evaporation occur, the rate of evaporation become more compared to the rate of diffusion. The rate of evaporation will be more compared to the rate of diffusion because there will be no enough water content to maintain the continuous layer over here. But in the previous you can see that the continuous film formation at that particular surface, that is evaporating surface, and the contents from the interior traveled by the process of diffusion in order to maintain the continuous filament, uniform filament, the evaporating surface, and that is in the second phase. Rate of diffusion becomes equal to rate of evaporation. But in the following year period, you can see that there is no maintenance of the continuous film, and drying part began to appear, and the drying rate begins fall off. And point D at this particular graph, you can see over there, from that starting to the point D, that is referred to as a second critical point, while C was termed as first critical point or moisture point. And the second one, that is the second falling rate period, that is the subdivision of the falling rate period, at the time corresponding to D in the graph, you can see it is on the slide number 19. If we will consult again, you can see that is DE, that is the second falling rate period. At the time corresponding to DE in the graph, during this period rate of drying falls even more rapidly than the first falling rate, and no film is present on the surface. Similarly, that was in the first falling rate period, but here the drying rate will be falls more rapidly compared to the first falling rate period. And again, there is no film formation, earlier formation of the moisture present on the evaporating surface, and at the end the drying rate becomes 0, and the moisture content of solids at this point, that is point T, it is referred to as equilibrium moisture content. And at point E, you can see in the graph that at point E, that is the point E, that is equilibrium moisture content, and the drying rate you can see that was represented from the y-axis. The graphical representation show that at point E, the drying rate becomes equal to 0. It means that there is no further water content to be removed, and at this stage the solid material having the moisture content that is similar or equal to the environment or surrounding. The surrounding having the similar moisture content as that is in the particular solid material that we have dried at point E, that is termed as equilibrium moisture content. And point E is termed as equilibrium moisture content, abbreviated as EMC, because at the end the drying rate becomes equal to 0 and the moisture content of the solid at this point is referred to as equilibrium moisture content. And what is meant by the equilibrium moisture content that we have defined in the previous lecture as well, but I am going to explain a little bit to you as well. That EMC, that is the abbreviation of the equilibrium moisture content, that is defined as the mass of water per unit mass of dry solid when the drying limit has been attained by use of air at any given temperature and humidity. The second following the period of hot air is there. You can see but rate of drying is directly proportional to rate of diffusion of water vapor. Finally, references you can consult the Lieberman, the book entitled as the Theory and Practice of Industrial Pharmacy, third edition. Pages consulted over there is 52 to 54, and as well as Art and Pharmaceutics, the Science of Dosage Form Design, second edition. Pages consulted over there is 383. Thank you all for your attention. Just to overview the today's topic. Entitled as Behavior of Solids During Drying. That may be entitled as Drying Rate Curve. What will happen to the solid material during the process of drying? The drying rate curve that may be entitled as typical drying cycle. In this particular lecture, first of all, we have derived an equation, a formula for the determination of the drying rate. That's how we have to calculate the drying rate. For this purpose, we have to take a sample and we have to suspend it, the wetted material on a weighing balance from a drying cabinet, and then we have to measure the weight of the sample after drying as a function of time. We have to note the time as well as the drying weight and moist solids weight as well, and then we have to put in the equation that the drying rate is equal to weight of water and sample and dividing it by the time and the weight of the drying solid. And the drying rate curve may be obtained by plotting a curve of FMC rate of free moisture content on x-axis, and while the y-axis we have put drying rate as well. Then we can observe the different drying patterns depending on the external condition and internal mechanism of fluid flow. A typical drying cycle can be divided into initial adjustment period, constant rate period, as well as the falling rate period. And there is a graphical representation. You can see on the y-axis the drying rate, the x-axis is the moisture content or free moisture content. It can be divided into the three distinct zones: initial adjustment period, constant rate period, the second one, and the third one, that is the falling rate period. And the falling rate period may be subdivided into two phases: first falling rate period and the second falling rate period. And there are certain other terminologies used in this discussion we have discussed, that is critical moisture content, second critical moisture content, and equilibrium moisture content. And we have planned initial adjustment period, that is in the cause of AB curve, and it is also termed as heating up period. What happened to the material during this stage? We have planned and a continuous film formation, initial adjustment period diagram, constant rate period, during which the rate of diffusion becomes equal to rate of evaporation, and the moisture evaporating from the surface is replaced by the water diffusing from the interior of the solid material, and here the rate of diffusion becomes equal to rate of evaporation. At one stage, uniform perimeter is difficult because of the depletion of water and the coarse capillaries, and the drying part starting appearing because of the complete film formation is not possible, and that areas, and these areas are termed as dry spots. At one stage, rate of evaporation becomes equal to rate of diffusion. After that, of critical mass of content, the drying rates start falling, and it's subdivided into the two phases. First falling rate period is also termed as period of unsaturated surface drying. That is the time corresponding to CD in the curve. Here in this diagram you can see in the first falling rate period the dry spot starting appearing and no continuous film formation over the operating surface, and the dry spots beginning at that stage, and rate of drying begins falling, and at this stage rate of evaporation is more compared to the rate of diffusion because there is no much water contents which have diffused from that particular interior toward the evaporating surface, and this is termed as first falling rate period. And the point D in the graphical representation is referred to as second critical point. And the second falling rate period, it is time corresponding to D in the graphical representation, and in this stage the rate of drying falls more rapidly compared to the first one. Because of the first falling rate period, there is much less quantity of water content in the material and no continuous film formation is present on the operating surface. When dry becomes equal to 0 and the points E, that is termed as equilibrium moisture content, or moisture content of the solid at this stage becomes equal to 0, and finally we have defined the EMC, that is equilibrium moisture content, as well as the reference book consulted for the preparation of this lecture. We will discuss this topic in the online Google Meet session as well. You can download the material from the portal. The graphical representation is also mandatory. If you understand this graphical representation, what is meant by from the AB and the BC points and the BC on CD and DE, and on the x-axis what to be shown and the y-axis what to be shown. And the typical drawing cycle 3 phases or testing zone. It shall be easy for you to discuss this topic in detail. Remember, you can see in the book figure number 3, that is a period of drawing that we have discussed, that is that's on the moisture content on the x-axis, while on the y-axis to drawing weight. You can see figure A, or rather than figure B as well. That is also the presentation, but here you can see this is a drawing weight,
Here it is shown on the x-axis, while on the y-axis you can see the master content. You have to discuss this one, that is the period of drawing, by keeping a master content on x-axis while on the drawing grid on the y-axis. Master content already explained in the previous lectures.